of the main points across. And we're not doing that because we don't have class. Okay, but some students, a few in the two classes that met today, were familiar with a histogram. A histogram is a kind of you can call it like a bar chart or a bar graph that shows the frequency of people or of measurements or people's responses or test scores within certain numerical categories. And the more responses in a particular category, which is called a bin, the higher the rectangle you draw on top. And you can read off of the scale on the left-hand side, just how many that's supposed to represent. For example, in this one here, it looks like the frequency, there was 9 in the bin that showed heights in between 149.5 and 159.5. And we're not making histograms here. But the point is, these all represent distributions, right? Distributions of measurements amongst people most of the time, but it doesn't have to be people. Shouldn't really say that. But notice that each one of these has a slightly different shape. Okay. Now, if I divide the frequency by the total number of occurrences in here, this turns into a probability chart or a probability distribution. Okay, what we're doing today is we're looking at how a normal curve is a mathematical model for a probability distribution, a histogram, which is considered to be quote unquote normal. Now, by normal, it means if we would have made our histogram, it would have had one peak in the middle. So the highest bar would have been in the middle, and then the bars on either side would have fallen away. Pretty much the same because it's symmetric. So you call a distribution like this unimodal because it just has one peak in the middle, and symmetric because it's the same on the left as it is on the right. Okay, so that's generally what a normal distribution looks like. Now, normal distributions are the results of random processes. A lot of times, people will use like test scores. Let's say the average height of a group of people or the weights of a group of people. I'm saying I would consider how long it takes me to drive to school every day to be a random process. Clearly, there is an average time that it takes me to work, and probably most days that's pretty much where I'm at, right? That would be the mean. Okay, if I have some occurrences where it takes me longer than average, but less than for the mean, and some occurrences that take me less time than average, but again, that's a little bit lower than the bar for the mean. Why is it random how long it takes me to get here? Well, think of the things that affect how long it takes me to get to work. How many traffic lights do I hit? What's the traffic like? What about the weather? Maybe I'm driving more aggressively one day than another. All those things are kind of random inputs to the total length of time that it takes me to get to school. And for that reason, I would expect that if I could make a distribution of, let's say, a month of driving times, it would probably look pretty close to this one right here. So that's normal. Now, we're going to use a normal model, a normal curve, to approximate normal distributions. In this histogram, which has got nothing to do with anything that we are dealing with, this blue line in the background, that's a normal curve, right? That's a normal curve. And you can see it's got a pretty good approximation of the shape of the distribution behind it. Not perfect, right? There's some places where it's a little bit low. There's some places where it's a little bit high. But for the most part, it looks like it's a good approximation. So just like we used functions to model our scatter plots, we can use a normal distribution to model, a normal curve, sorry, to model probability distributions. And the shape of a normal curve is called a bell curve, because it's kind of shaped like a bell, right? If you ever take a AP Psych class, I'm sure that you will talk about a book called The Bell Curve, which came out in the early 90s, about using a normal model to model IQ more than anything. It's kind of controversial in its day. If you Google it, you'll see probably a lot of negative comments about the book The Bell Curve. But the bell curve is actually has a mathematical equation that generates it, right? It's called a Gaussian equation or Gaussian function. You can see the two values, the two independent variables that you plug into this are the mean and the standard deviation, right? Both things that we studied in the last lesson. And you can see there's a couple other things that we're familiar with. It's got pi in it. We know that. It's got e in it, the base of a natural logarithm. It's an exponential function. It's e to the negative something, right? It's not exponential growth or decay, but all exponential functions are not necessarily growth or decay. So this is exponential. Sorry, this is an exponential function, a Gaussian function, and it makes this curve right here. Now, if you notice on the curve, in the middle of the curve is opening down, right? But if you go over onto the sides, it looks like it's opening up. So if you really want to draw a bell curve correctly, what you notice is the mean is always in the middle, plus 1 standard deviation to the right should be exactly the point where the curve stops opening down and starts opening up. It's called a point of inflection. And in calculus terms, that's a second derivative, which is kind of interesting because notice now that when we calculated standard deviation, that was quite a complicated formula to come up with an average of spread, right? But it's important to this curve, right? It's exactly 1 standard deviation to the right, you get this point of inflection. All right, so once you know what the 1 standard deviation is in any direction, then you could just like sketch out standard deviations to the left and to the right. They will pretty much always be 3 to the right and 3 to the left, right? And if you have to sketch a normal curve, again, you could be a little careful with it and try to make your curve start bending the other way, right about 1 standard deviation to the right. In the end, anything is okay. I've seen students that basically draw the normal curve like it's a semicircle, which is clearly not even close, but it'll do the job. So the first thing that we got to know about the normal curve is because it has a very precise mathematical equation behind it, that in fact there are some standard percentages of the amount of the data which is in between the standard deviations under the curve. And again, we are going to interpret the area under the curve as a probability. The probability of data falling between 1 standard deviation to the left and 1 standard deviation to the right of the mean is 68%, or in this case they've used tenths, so it's 68.2%. Right? The probability of our data falling between -2 standard deviations and +2 standard deviations, 95.4%. And in between -3 and +3, 99.7%. Okay, that's called an empirical rule, right? I taught out of one book once that called it the 68, 95, 99.7 rule. Which as a title, if you can remember it, will at least tell you the percentages. Now remember that the normal distribution is symmetric, right? It's got to have exactly the same area under the curve to the left as it does to the right. So you can take that 68%, which is in between these two, and divide it in two. There's where the 34.1 and the 34.1 come from, right? If I do the same thing, right, take this 95.4%, subtract 68.2%, and divide by 2, you're going to get 13.6 on either side. And the same thing, that's how we come up with this 2.15%. Now the 2.15% actually, that goes on forever to the right and to the left, because the normal curve never touches the x-axis. It actually goes on forever. Right? There's always a teeny, teeny little probability that a piece of data might end up in a really extreme position. Kind of like winning the lottery. You know, not going to happen very often, but you can't rule out the possibility. Okay. So again, this is like 90% of what we've got to get out of this. So we can do probabilities based on the empirical rule, and I'm using the same chart. You know, what this says here in the parentheses is saying, what's the probability that X, right, which is a piece of data, would fall between the mean minus 2 standard deviations to the left, that would be here, and the mean, which would be here. Okay, well, let's see. It's 13.6% for this block, and it's 34.1% for this block. So if I add them up, I'm going to get 47.7%. So if you're asked the question, what is the probability, you would probably write it as 0.477, because probabilities are between 0 and 1, as we learned on day 1, okay, of this unit. If you're asked for what percent, then by all means you say 47.7%. Okay, so let's try a few more of these. I said you try in this, but we actually did these together in class. Right? The probability of X being less than the mean, right, here's the mean, meaning what percent of the data is to the left of the middle? 50%, 0.5. And what percent is greater than the mean? 50%. Okay, what percent is in between the mean and 2 standard deviations to the right? Okay, well, we kind of did this one to the left already, so we have to add those up, and it'd be 0.477. Okay, last one. Change color. The probability that X is greater than or equal to the mean plus 1 standard deviation. Well, the mean plus 1 is here. So that's like saying, what's the probability of being to the right of that point? Okay, well, now we're going to add up 13.6 plus 2.15, which will be 15.75%, which will make this 0.1575. Right, so here's a word problem normal calculation. Scientists conducted aerial surveys of a seal sanctuary and recorded the number X of seals they observed during each survey. The numbers of seals observed were normally distributed with a mean of 73 seals and a standard deviation of 14.1. Find the probability that at most 50 seals were observed during the survey. So the standard procedure for doing this is that you should draw a curve so you know what it is you're looking at. Draw and label a curve. Okay, what goes right in the middle of the curve? The mean. Right? And in this case, the mean is 73. Okay, about halfway down the slope there, right where it should be the point, inflection point, right? I should be plus 1 standard deviation. And that would be plus 14.1, so that is 87.1. And then I can go the same distance again. That'll be plus 2 sigmas, and that'll be 101.2. If I go the opposite side, subtract 73 minus 1 standard deviation, 14.1. Let's see, that'd be 58.9. And if I go one more, that'll be minus 2 standard deviations. And that looks like it'll be 44.8. So when you label the curve, you'll see the mean, right? The mean is there. You don't really see the standard deviation. You could figure it out by the numbers that are plotted, right? I needed to know that 14.1 to figure out these numbers. Okay, so now we want to know the probability of that at most 50 seals were observed during this thing. Well, let's see, find 50. 50 would be somewhere in between the 44.8 and 58.8. Okay, so let me draw a line in there and say that's 50. So when it says find the probability of, what they're asking for is what's the area under the curve, right? What is this area? This area that ends on the right-hand side is 50. On the left-hand side, it goes on forever, right? So I'm going to show you how the book shows you how to do this, but understand that the book was written in 2007 or published in 2007, and actually we don't do it this way anymore, although I wouldn't be surprised if an AP stats class or some other kind of lower level stats class you might end up having to do this, right? Since this 50 is not exactly on one of our whole number of standard deviations above or below the mean, then we have to calculate the z-score to do this. Okay, we need to calculate the z-score for 50. Remember, I think I've got this on the next slide, right? The z-score is the data value, of which our case is 50, minus the mean divided by the standard deviation, right? So 50 minus 73 over 14.1. Okay, do the math. Negative 1.6, although I have to say I rounded that off a little bit. Okay, it had more digits after that. Okay, now the way we used to do this stuff is you would have what you call a standard normal table to look up a z-score, and you would know that this would be telling you the probability of x being less than z. Right? Always in this table, it's telling you the probability of x less than the z-score. But, you know, in our problem, in fact, that's what we want. Now, if we wanted to know the area, or, you know, the probability of seeing more than 50 seals, then we would still have to calculate the z-score of negative 1.6, and we would still find the probability, which is the value to the left of negative 1.6, and then we would do 1 minus. Okay, so anyways, in this case, for the negative 1.6, the probability, the area under the curve, negative 1.600 is 0.0548. Right, which is about 5.48%. Okay, now we don't have standard normal tables to look up z-scores anymore. Instead, we have our calculator. And our calculator, in order to do this with the calculator, then you go second vars 2, right? Second vars, and then in this menu, which will show up, you want to hit 2 for normal CDF. Okay, that means cumulative distribution function, which means it's going to be adding up the area underneath the curve, in between two x values, right? The normal PDF is for a point. It's only going to tell you the height of the curve at one point. That would not be of interest to us, so we don't use that. Now, when you hit the 2, you get a menu that looks something like this, right? The lower is asking you for the left side of that shaded area on the normal curve. The upper is asking you for the value on the right side. The mu is is the mean, and the sigma is standard deviation, like we've learned already. Now, for our problem, again, if I go back, the left side of our interval here, right, this here is undefined, right, because this goes on forever. But you got to have something in the normal CDF entry right here. So usually what you do is, if it goes on unlimited to the left, you put in a big negative number, something that's well beyond multiple standard deviations from the mean. Okay, you don't necessarily need to say -1 times 10 to the 99th. That'll certainly do the trick. But understanding that, 99.7% of the area is between 3 and -3 standard deviations, we don't really need to go that far. You could probably have put in 0 here, and you're going to get the same values anyways. So anyways, second vars 2, this is for our problem. Okay, -1e99 is the lower bound, 50 is the upper bound, 73 is the mean, 14.1 is the standard deviation. Let me do that here on my calculator. I want to clear this. Second vars 2.
Attention students, if you plan to ride the activity bus, you must have a pass from your teacher or sponsor. Buses will leave from the front of the building in 10 minutes. Thank you.
Sorry, that was a message. Okay, so everything's in there. Okay, paste those values into the function, and there's your answer. 0.0514. Okay, now that's not exactly the value that I got when I looked it up in the z table, because I rounded when I had -1.6, and there were some digits that came after, but it's still about 5%. Okay, so again, if there is no lower bound, use a really big negative number or something that's just well beyond the range of the mean. At least 5 or 6 standard deviations to the other side. And the same thing could happen for an upper bound. If you don't have an upper bound, if it's to the, find the probability of x greater than something, then you're going to have to fill in a really big number for the upper, mean standard deviation. Okay. Now, one thing to notice that in this one right here, when you have 0 for the mean and 1 for the standard deviation, that's called a standard normal distribution, which is, in the end, why we have a standard normal table to look up z-scores. Okay, so if you did everything with z-scores, then you'd have a mean of 0 and a standard deviation of 1. Okay, now I'm going to do a few of these problems. All right. These are on a worksheet that I gave you in class to work. I think the worksheet, it'll agree with this here. If you get the downloaded version, the things I scratched out aren't scratched out anymore. But that's okay. Whatever you get is fine. Okay, 2,000 freshmen at State University took a biology test. The scores were distributed normally with a mean of 70 and a standard deviation of 5. Label the mean and 3 standard deviations from the mean. I'll go back to my blue. So the mean is 70, right? Right in the middle. Standard deviations, 75, 80, 85, 65, 60, 55. Okay, you should have that in front of you before you get started. You might have to hand draw your own normal curve, but whatever you can, it might help you to draw the picture. What percentage of the scores are in between 65 and 70? Okay, well, 65 is exactly one standard deviation below the mean, and 75 is exactly one standard deviation above the mean. So we should know those percentages of the empirical rule, right? We should know that that's 68%. Without using a calculator, we can know that. Okay, now, you could use a calculator if you have it in your hands. I mean, second distribution to, if I said 65, enter, 75, enter, 70, enter, and 5, it ought to give me something close to 68%, and it does, 0.6826, so 68%. Okay, what percentage of the scores are in between 60 and 70? Okay, that would be in this area. Okay, we kind of did that one already. Remember, that was when we added up the 34.1 and 14.6, I think it was. The percent was 47.7%, rounded to the tenths. But of course, you could put it in your calculator. Second, bars 2, and we'll go 60, 70, and those don't change. 47.7%. Look at that. Okay, last one. Scores between 60 and 85%. So 60 to 85. Right, so now we got to be going back to the empirical. If we don't remember it, we know that this was well, I could say between 60 and 80, that's 2 standard deviations to either side. How much is it? Right, that was 95 point something percent. Let's just say 95%. And I think they had on this 2.15. Wasn't that right? 2.15%? As I remember. If I'm not sure, just put it in the calculator. Second distribution, 2. So this is 60 to 85.
Attention students, last call for activity buses. If you plan to ride the bus, please bring your pass and come to the front of the building. Thank you.
So it looks like it's 9.75%. Or sorry, 97. Get this back again. 97.5, 97.6%. Okay. Okay, now we kind of already did this, but there's a reason I scratched these out on the worksheet, because they were all asking, these whole numbers of standard deviations to either side. And the fact is, it won't always be that way. Let me relabel this. 70, 75, 80, 85, 65, 60, 55. So if we want to know this probability of a score less than 54, well, 54 would be here. So I got to find the area to that side. And it's not a whole standard deviation, so I can't use the empirical rule. I'm going to have to use the calculator. Second, vars 2. And this time, the lower bound is going to be something small. I'll put 0. The upper bound is going to be 54. And the rest is there. 6.87 times 10 to the negative 4th. Which is a decimal. If you want to turn it into a percent, you'd multiply times 100, 6.87 times 10 to the negative 2, which is 0.0687%. Okay, what percentage of scores is greater than 79? Okay, 79 is here, right? So now I have to use the left bound of 79. And the right bound, it goes on forever, so just put a big number. How about 200? .0359. Which as a percent is 3.59%. Okay, the next two questions are a little bit different. Okay, they're not asking for the percent. They're asking for how many biology students scored in a certain range, according to the model. Okay, well, in order to answer that kind of question, you got to know how many biology students took it. It was 2,000. Right, so first I need the percentage in decimal form, and then I need to multiply times 2,000. Now we've done this 60 to 70 several times now. We know it's 47.7%, but I'm just going to do it in the calculator because it's actually easier to do it that way. Is just bring up the calculator, second vars 2. Okay, between 60 and 70 means my lower bound is 60. My upper bound is 70. Same mean, same standard deviation. Right, there's the decimal percent, 0.477. Okay, we've seen that before. Now, to finish, multiply times 2,000. $954.49, which, is slightly less than 954.5, which would round to 955. So if you're hung up about that you can't add, the number of students isn't going to be a decimal, let's say 954. So again, it's 2,000 times 0.477 is approximately 954 students. And then one more. Approximately how many scored between 56 and 61? Second vars 2. 56, 61. The rest is the same. 0.033, right? So now we've got to multiply that times 2,000. 66.75, let's call it 67 students. Okay, so that is the normal curve, the normal distribution. And again, the homework was a worksheet of